Welcome, curious minds, to the deep dive. Have you ever found yourself interacting with a large language model? Maybe you're asking it to draft a complex email, generate creative code, or even brainstorm entirely new ideas and felt that almost magical sense of wonder?
Oh, absolutely. It happens all the time.
One moment you're staring at a blank screen, and the next, this AI has produced compelling, coherent text that feels incredibly human, sometimes startlingly insightful. It's truly like having an endlessly patient, incredibly knowledgeable assistant right at your
It
fingertips.
really is.
But here's the million-dollar question. How does it do that? What's the secret sauce that allows these remarkably capable systems to understand, process, and generate human-like language with such fluency?
It's a question many of us have pondered, and it truly does seem to defy simple explanation at first glance. The seamless interaction belies an incredibly intricate architecture and a fascinating, almost organic learning process happening beneath the surface.
Absolutely, and that's precisely our mission today. Okay, let's unpack this. We're going to take a deep dive into the foundational concepts, the intricate mechanics, and the cutting-edge techniques that power large language models, or LLMs.
Right.
We'll explore everything from how they initially absorb vast amounts of information to how they're fine-tuned for incredibly specific tasks, aligned with complex human values, and optimized for real-world use at scale.
Think of it as a journey from just raw, unstructured data.
To truly intelligent conversational AI. Yeah.
Our insights for this deep dive come from a fascinating collection of cutting-edge research, including a comprehensive review paper focusing specifically on the pre-training and inference stages for LLMs.
Okay.
So this deep dive should offer you a shortcut, really, to understanding not just the what, but crucially the why behind the latest advancements in AI language models, hopefully giving you those aha moments you crave when the pieces suddenly click into place.
Fantastic. So, if we're tracing the life of an LLM, where does it all begin? It can't just pop out of thin air, fully formed and brilliant, right? How do these models first learn to speak, to understand the very fabric of human language?
You're absolutely right. It's a long journey, and it all starts with what we call pre-training. This is the initial large-scale learning phase for LMs, arguably the most critical.
Pre-training. Okay.
Imagine you've given a brilliant student access to the largest library conceivable, billions of books, articles, online conversations, code, historical documents, scientific papers,
Yeah.
you name it. Virtually the entire written digital corpus of human knowledge.
Wow.
But instead of teaching them specific subjects, you simply tell them, read everything, absorb, find the patterns. They're not learning any specific skills yet. They're just building an immense foundational understanding of language itself.
And the facts embedded within it.
Exactly. The facts, the relationships between ideas, all expressed through words. It's about soaking it all in first.
That makes sense. It's like building the most comprehensive dictionary and encyclopedia imaginable, all inside one system. Now, traditionally, in machine learning, I know there were sort of two main ways to approach this kind of initial training. The first, the more established method, is supervised pre-training.
Precisely. In supervised pre-training, a neural network is trained on existing labeled data for a very specific task.
Labeled data being the key.
Right. So if you wanted a model to classify movie reviews, you'd feed it millions of reviews that humans have already painstakingly labeled as positive, negative, or neutral. The model learns by identifying patterns that lead to those specific labels.
The advantage there seems clear. It's straightforward, it follows well-understood machine learning paradigms, and well, if you have the data, it works.
It does work.
But here's the major challenge, right? As neural networks grow exponentially in complexity, the demand for labeled data absolutely skyrockets. And collecting vast amounts of high-quality human-labeled data for every single possible task, that becomes incredibly difficult, time-consuming, and astronomically expensive.
It's a huge bottleneck. It simply can't scale to the ambitions of truly large models. Which brings us to the true game changer, and really the dominant paradigm for how modern LLMs acquire their immense capabilities.
Yeah.
Self-supervised pre-training.
Self-supervised. Okay, this is where it gets interesting.
Yeah, here's where it gets really interesting, because the model learns without any human intervention in the labeling process.
So instead of needing humans to explicitly label data, the model learns directly from unlabeled text. How? It essentially creates its own prediction challenges, or supervision signals, straight from the data itself. No human labeling needed.
That's the core idea. How does it even work? Well, you can think of it like this. Imagine that diligent student again, but this time, instead of a teacher giving them explicit instructions or correcting their homework, they learn by constantly quizzing themselves.
Okay.
As they read an enormous number of books, they might cover up the next word in a sentence and try to predict what it should be.
Ah, like fill in the blanks.
Exactly. Or they might mask out a random word in the middle of a sentence and try to fill in that blank. By repeatedly doing this across billions or even trillions of words, they start to learn the intricate patterns, the grammatical rules, the semantic relationships.
And even the nuances of how language expresses facts about the world.
Precisely. They're building a deep understanding purely through self-correction, without a single explicit label from a human.
And the power of this constant self-generated prediction is truly profound. What's mind-blowing is how this seemingly simple act of predicting the next word, repeated billions of times across vast data sets, allows these models to distill, well, a certain degree of general knowledge about the world.
Yes, about its facts, its relationships. It's not just rote memorization. It's the emergence of something akin to understanding, purely from statistical patterns.
Which feels like a profound leap, doesn't it, towards more advanced forms of artificial intelligence, showing us that intelligence can arise from, well, unexpected places.
It really does. Now, when we talk about LLMs and their foundational structure, one architecture stands above all others as absolutely critical: the transformer.
Right, the transformer. You hear that name everywhere.
You do. Most pre-trained models in natural language processing, especially LLMs, are built upon the transformer architecture. Its revolutionary design, particularly its attention mechanism, gives it an unparalleled ability to handle long-range dependencies in text.
Meaning it can connect ideas from the beginning and end of a long document.
Exactly. It can understand how a concept introduced way back on page 1 relates to a detail found much, much later. That's absolutely crucial for genuine language comprehension and generation.
Okay. And within this powerful transformer family, I understand there are different flavors specifically designed for pre-training, each with a slightly different approach.
That's right. Tailored for different ultimate uses. The first flavor is what we call decoder-only pre-training. This is the architecture you find in language models like the GPT series.
GPT. Okay.
The core mechanism here is that the model predicts the distribution of tokens at a given position, based only on its preceding tokens. It's a strict left-to-right generation process, always looking backwards, never forwards.
Right. So if you give it the cat sat on the ooh, it's trying to predict Matt, but it doesn't get to peek ahead at Matt when it's deciding the. It's truly generating output one token at a time sequentially.
Exactly. The core task for these models is called causal language modeling, or CLM. It's all about predicting the next word in a sequence.
Causal language modeling, like trying to write a sentence without knowing the ending.
Pretty much. The model generates the, then based on the, it predicts the out, then based on the cat, it predicts sat, and so on. Each word prediction is causal because it only depends on what came before it, building the sentence piece by piece.
Okay, so that's decoder only, the generator. What's the other side?
Then you have encoder-only pre-training, exemplified by models like BERT. These models are built to learn rich, bidirectional representations of input sequences.
Representations for understanding tasks, right? Not direct text generation.
Precisely. If I'm building a chatbot that needs to generate fluent responses,
Yeah.
I'd lean towards decoder only.
Yeah.
But if I need to analyze text, like understanding the sentiment of a review or identifying key entities within a legal document, then encoder only is my go-to.
So decoder only models are like masterful storytellers.
Always looking to spin the next part of the narrative one word after another. Yes.
While encoder only models are more like brilliant detectives.
That's a great analogy. You give them a paragraph and they don't add to it, but they can tell you everything about what's already there, who's involved, what's being discussed, the tone, the key takeaways.
And that deep understanding comes from their primary task, which is masked language modeling, or MLM.
Exactly. That bidirectional understanding is key, and MLM is how they achieve it.
And the masked language modeling task is quite clever. Some tokens in the input sequence are randomly masked out, replaced with a special mask token, and the model is then trained to predict what those masked tokens should be.
Right, like if you feed it the puppies are masked outside the house, it has to figure out frolicking or maybe playing.
And crucially, unlike the causal language modeling in decoders,
MLM allows the model to use all unmasked tokens, both left and right context, for prediction.
so it gets to see the whole sentence except the masked word.
Exactly. It can look at the words before and after the mask to infer the missing word, creating a truly bidirectional understanding. which is incredibly powerful for tasks that require deep comprehension.
And BERT's masking strategy isn't just random, it's quite specific, isn't it? Designed to maximize learning.
It is. It selects 15% of the tokens in a sequence for potential masking. Then, of those selected tokens, 80% are replaced with the actual mask token.
Okay, 80% get the mask. What about the other 20%?
Let's get a twist. 10% are replaced with a random token.
A random word. Why?
It makes the prediction task harder. It forces the model to generalize better and not just learn to rely on seeing the mask token. It has to consider the context even more carefully.
Interesting. And the final 10%?
The final 10% are actually kept unchanged.
Unchanged, so it sees the real word.
Yes, this encourages the model to learn from easier evidence, too, when the token is present. It helps balance the learning. So for a sequence like CLS, it is mask. SEP, I need mask hat. SEP, it might predict raining and using all this context.
Very clever. And I heard about a variation called span masking.
Yes, span masking. Instead of masking individual words, consecutive mask tokens of span are replaced by a single mask, or sometimes special sentinel tokens like X or Y.
So like the puppies are X outside Y.
Exactly. The model then has to predict the entire phrase for X, like frolicking, and maybe the house for Y. It forces the model to predict multiple tokens from a single mask point.
So it's not just guessing one word, but a whole chunk.
Right. This teaches the model to understand not just individual words, but the relationships and coherence between words in a sequence. It makes its learned representations much richer, especially for tasks that require generating longer, coherent phrases. It's a bit like how machine translation systems handle complex word-to-phrase mappings.
Okay, so we've got our master storytellers with decoder-only models and our brilliant text detectives with encoder-only. But what if you need a model that can do both, understand an input, and then generate a new related output, like translation or summarization?
That's where we bring in the best of both worlds, encoder-decoder pre-training.
Makes sense. Combine the two.
Exactly. These models combine both an encoder, which focuses on understanding an input prefix, and a decoder, which then generates the subsequent sequence based on that understanding.
How are they trained?
They can be trained directly on examples like prefix subsequent sequence, where the encoder learns the prefix's meaning and the decoder learns to continue it. Or they can also be trained via masked language modeling, similar to BERT, usually on the encoder part.
And this architecture is ideal for sequence-to-sequence problems.
Precisely. Machine translation is the classic example. Take a sentence in French. The encoder understands it, the decoder generates the English equivalent. Summarization is another encoder reads the long text, decoder writes the short summary, question answering, dialogue, anything where input is transformed into a different, coherent output.
Now, beyond just masked language modeling and causal language modeling, are there even broader pre-training tasks that contribute to an LLM's understanding, pushing the boundaries?
Oh yes, researchers are always experimenting. One interesting method is permuted language modeling.
Permuted, like shuffled.
Kind of. Instead of just predicting the next word or masked words, this approach shuffles parts of the input sentence and then tasks the model with predicting tokens sequentially, but based on a randomly selected context from the shuffled sequence.
Why shuffle it?
It forces the model to understand the relationships between words and phrases, even when their natural order is disrupted. It makes the model more robust to variations in sentence structure and helps it grasp underlying semantic connections more deeply.
Okay. What else?
There's also discriminative training. Here, the supervision signals come not from predictions, but from classification tasks. The pre-training model is actually integrated into a larger classifier system and trained alongside it, aiming to enhance classification performance.
So it learns to classify things as part of its basic training.
In a sense, yes. It embeds that classification understanding directly into its foundational knowledge.
And another one mentioned is denoising autoencoding.
Right, denoising autoencoding. This is primarily for encoder-decoder models. The input is a corrupted version of a sequence, maybe with noise added, words omitted, characters swapped, and the model's job is to reconstruct the original clean sequence.
Why make it harder like that?
It helps the model learn robust representations that can handle imperfect or noisy data. Makes it more resilient in the real world, where text isn't always perfect.
Okay, so we've covered how these models absorb vast amounts of knowledge through all these different pre-training techniques. It's quite a process. But once they've devoured this immense digital library, how are they actually used? They're rarely deployed raw, right? A model just predicting the next word isn't immediately useful for, say, writing my email.
Indeed. Because while pre-training gives them this immense, almost encyclopedic knowledge, it's like having a brilliant but uncut diamond. To truly shine, it needs polishing and cutting for specific purposes.
And that polishing is fine-tuning.
Exactly. Pre-trained models are adapted to specific natural language processing tasks. Their vast general knowledge gets specialized for a new, more focused purpose.
Like, for example, text classification, sentiment analysis, maybe.
Perfect example. You want to know if a movie review is positive or negative. You take that giant pre-trained LLM and then you fine-tune it on a data set of reviews that are specifically labeled for sentiment. Often the representation of a special token, like CLX, which capture the essence of the whole sentence, is used to make that final classification.
It's like taking a generalist doctor and training them to be a heart surgeon.
A good analogy. Or consider sequence labeling. Here, you assign a label to each token in a sequence.
Like part of speech tagging, noun, verb, adjective.
Exactly. Or named entity recognition and NAIR, identifying names of people, places, organizations in a text. The pre-trained model gives powerful initial representations for each word, and fine-tuning teaches it the specific labeling rules for your task.
And what about text generation using these principles, even with something like BERT, which is an encoder?
Right. While BERT itself is an encoder, its pre-trained understanding is incredibly valuable. You can use its principles, or even the pre-trained BERT model itself, to initialize the encoder part of a larger encoder-decoder system. Then you pair it with a decoder and fine-tune them together for generative tasks like machine translation, summarization, question answering, or dialogue generation. You leverage its deep understanding to produce coherent, relevant text.
What really fascinates me is their multilingual and cross-lingual capabilities. How does that work?
It's quite elegant, actually. These models can be pre-trained on vast amounts of multilingual data, often sharing a single, massive vocabulary that includes words from many different languages.
One giant vocabulary for everything.
Yes. This means the model learns shared representations and relationships across different languages. It might notice similar sentence structures or concepts expressed similarly in English and French, for instance.
And the huge benefit of this is code switching, right? Where people mix languages in one sentence.
Exactly. LLMs trained this way can inherently handle texts that seamlessly switch between languages. That example sentence, yeah, mixing Chinese and English, the model can process and understand that just as easily as a single language sentence.
Because to the model, yeah and hiking are just tokens in its big vocabulary.
Precisely. It essentially creates a new internal language encompassing all the languages it has processed. It allows for really fluid understanding across linguistic boundaries.
Now, as researchers built these, they found something crucial. Size matters. The drive for bigger models.
Oh, absolutely. It was one of the most powerful discoveries. They consistently found that simply increasing model parameters, making them deeper, adding more layers or wider, increasing the hidden size dramatically improved performance for BERT-like models and beyond.
We're talking billions of parameters, right?
Yes, models scaling from millions to 1.5 billion, 3.9 billion, and now hundreds of billions or even trillions of parameters. More parameters generally meant more capacity to learn and store knowledge.
But that scaling introduced entirely new problems, didn't it?
Formidable challenges. Training these huge models often becomes highly unstable. They can struggle to converge, meaning they have trouble learning effectively.
It's not just bigger is better, then.
Not at all. It requires incredibly careful consideration of the architecture design, sophisticated strategies for parallel computation across potentially thousands of GPUs, and extremely precise ways to initialize the parameters before training even starts.
Like coordinating a billion-instrument orchestra, you said.
It's a good way to think about it. One wrong setting, and the whole training run can collapse.
And then there's the computational load during inference when the model is actually being used. How do you make that efficient?
Right. Inference has its own challenges. Researchers developed ingenious solutions like dynamic networks. These are designed for efficiency, allowing the model to adapt its computational pathway on the fly.
Like depth adaptive models.
Exactly. These can dynamically choose the optimal number of layers to use for a given input. If the model feels it is understood enough after, say, 10 layers, it can effectively exit the network early, skipping the remaining dozens of layers.
Saving a huge amount of computation.
Immense amounts. Similarly, length-adaptive models dynamically adjust the input sequence length, perhaps by identifying and skipping less important tokens or phrases. It's all about being smarter with resource allocation to get answers faster and use less energy.
This really brings us into what people are calling the era of large language models, training models on these massive data sets, trillions of tokens from the web, books, code, conversations. It really has led NLP research into, well, exciting times.
It truly has. For a long time, language modeling was maybe seen as just a foundational technique, important but perhaps not directly leading to truly intelligent systems.
But then they just kept getting bigger.
And as these models scaled beyond imagination, we saw the undeniable emergence of intelligent capabilities, systems that could learn general knowledge, reason, even create just by predicting words.
It really suggests a fundamental step towards more advanced AI, doesn't it? Systems showing genuine intelligence, not just clever algorithms.
Absolutely. And these powerful systems are now widely known as foundation models.
Foundation models, that term seems quite apt.
It is. The idea is revolutionary. A single, exceptionally well-trained LLM can now handle a vast number of diverse tasks and generalize to perform new ones with very little additional adaptation.
So one digital brain for writing code, summarizing legal briefs, and brainstorming marketing slogans.
Potentially, yes. It shifts the paradigm from building countless specialized AIs to training one powerful core that adapts. We're talking models like GPT-3 with 175 billion parameters, or newer ones like Falcon 180B, Llama 265B, Palem 450B, Gemma 7B, all trained on these truly immense data sets spanning trillions of tokens.
Right, so you have these incredibly powerful foundation models. The next crucial step is mastering communication with them. How do you tell this super knowledgeable digital assistant what you actually want it to do? That's where prompting techniques come in, right?
Exactly. Prompting is essentially how you guide an LLM's behavior. You give it instructions, questions, or examples.
Like giving specific directions.
Precisely. Think of it like giving detailed directions to that very knowledgeable assistant. You're not reprogramming it. You're just telling it what you want it to do with the vast knowledge it already has. You shape its output with your words.
And there are some general principles for designing good prompts.
Yes, and they're incredibly effective. First, specificity and detail are paramount.
So not just tell me about climate change.
Right. You'd use a prompt like, provide a detailed explanation of the causes and effects of climate change, including the impact on global temperatures, weather patterns, and sea levels. Also, discuss possible solutions. That level of detail gives the LLM a clear target.
Much more useful response that way.
Definitely. And you can take that a step further with audience adjustment. If you need to explain climate change to a child, you refine it. Explain climate change to a 10-year-old. Talk about weather, sea levels, temperatures. Mention things people are doing to help. Simple terms, under 500 words.
Tailoring the output significantly.
Yes, ensuring the language and complexity fit the recipient. Another key principle is leveraging prior knowledge. Including known, reliable context in the prompt generally improves results. It grounds the LLM.
Gives it a better starting point. And prompting works for lots of tasks. Classification, completion, code.
An incredibly wide variety. Text classification, positive negative review. Text completion, continue this story. Code completion, finish this function. It's very versatile.
But here's where it gets really interesting. That aha moment many of us had. In context learning, LLMs learning from demonstrations within the prompt itself without extra training.
It's quite remarkable. It's like showing a student a few examples and they just get it.
You have zero-shot learning first, right? No examples, just instructions.
Correct. Like, correct this sentence.
Yeah.
So you don't like the park. Output.
Mm.
The LLM often just knows how to do it from its pre-training. That's its inherent intelligence.
Then one-shot learning. One example provided.
Yes. Demo. Input. There was many reasons. Output. Many reasons. User. Input. She don't like the park.
Yeah.
Output. The model learns from that single demonstration.
And even more powerful is few-shot learning with multiple examples in the prompt.
Exactly. Crucial for new or complex tasks where zero-shot might fail. More patterns to infer from, better generalization, like giving a few case studies first.
Now, guiding them to think more deliberately. Chain of thought. CHOTI prompting.
This is fascinating.
It really is. The core concept is instructing the LLM to generate intermediate reasoning steps before the final answer. Show your work, essentially.
And the impact is huge, especially for things like math problems.
Drastic improvements. Take that classic apple problem. Jack has 7 apples, eats 2, gets 5 more, gives 3 away. How many left? Instead of just outputting 7.
A CHOTI prompt makes it say something like, okay, Jack starts with 7, eats 2, leaves 5, gets 5 more, now has 10, gives 3 away, leaves 7, final answer, 7.
Precisely. You see the entire reasoning process laid out. And the amazing thing is, often just appending the phrase, let's think step by step, to the prompt can trigger this.
That's the magic phrase.
Yeah, often works surprisingly well. It seems to activate the LLM's thinking ability, encouraging it to externalize its process. GoT helps significantly in mathematical, logical, common sense, symbolic reasoning, even code generation.
Going beyond that linear thinking, there's problem decomposition, breaking down complex problems. Yes, just like humans do, taking a big, daunting challenge and breaking it into smaller, manageable subproblems.
How does the LLM do that?
It can generate a series of subproblems. Each one might be solved by the LLM itself, acting in a different mode, or even by calling external tools like a calculator, a search engine, a code interpreter.
So it can use tools.
Potentially, yes. Then it combines the results from the solved subproblems to construct the final answer to the original complex question.
And these subproblems can be generated on the fly.
They can be generated dynamically, adapting as new information emerges. You could even have hierarchical decomposition breaking subproblems into even smaller parts, like a branching thought process.
And then there's self-refinement. LLMs evaluating their own work, like self-reflection.
It's a fascinating parallel. The model can evaluate its own initial outputs and then iteratively improve them.
How does that work in practice?
Well, first, the LLM generates an initial response, say a translation. Then the same LLM is prompted again, but this time to critically review that translation, evaluate accuracy, maybe suggest improvements.
Getting feedback on itself.
Exactly. Then, given this self-generated feedback, the LLM refines its original response, often leading to a significantly better output. It's an internal feedback loop.
And there's a related method, deliberate then generate, DTG.
Right. DTG specifically prompts the LLM to deliberate and identify potential error types or areas for improvement in an initial output before providing the improved version. It's like an internal editor pointing out flaws before rewriting. Pushes beyond simple rephrasing towards real conceptual improvement.
Okay, so these models can be incredibly smart, adaptable, even self-reflective. But there's a huge challenge, making sure they are helpful, harmless, and honest. The alignment problem.
Absolutely crucial. This is perhaps the most critical challenge beyond pure capability. Why? Imagine an LLM giving accurate instructions on hacking or spreading dangerous misinformation or generating biased, harmful content.
That's terrifying.
It is. Alignment aims to prevent that, ensuring these powerful AIs serve humanity responsibly and ethically.
So after pre-training, there are key alignment steps. The first is supervised fine-tuning, or SFT.
Right. SFT involves continuing the training of those pre-trained LLMs, but this time on new, carefully curated, task-oriented, and importantly, labeled data that reflects desired behavior.
And a common technique here is instruction fine-tuning.
Very common, very effective. LLMs learn from human-annotated instruction response pairs, like summarize this article, followed by a high-quality summary. This specifically aligns the model with following diverse human instructions effectively.
How does the training work technically?
Usually you concatenate the input instruction and the desired output into one sequence. During training, the learning signal, the loss, is computed only for the output part. And it's versatile enough to handle multi-round dialogue too, teaching coherent conversation.
But SFT has challenges. Data acquisition sounds tough.
It is. You need high-quality, substantial labeled data reflecting desired behaviors. Manual annotation is complex, requires careful prompt design, clear guidelines, rigorous quality control.
And it's still computationally expensive.
Yes, especially for the largest LLMs. Less than pre-training, but still significant. This drives research into parameter-efficient fine-tuning PEFT methods, which try to update only a small fraction of the parameters to save resources.
And there's the risk of catastrophic forgetting, the model forgetting its pre-trained knowledge.
A serious risk. If you fine-tune too intensely on a narrow data set, the model might lose some of that broad general knowledge, like the polymath forgetting other fields after specializing.
How do you mitigate that?
Things like regularization, stopping the fine-tuning early, using smaller learning rates, ensuring the fine-tuning data is diverse.
This leads to the superficial alignment hypothesis, the idea that SFT is just tuning the surface behavior.
Sort of. The hypothesis suggests core abilities come from pre-training. SFT primarily tunes the model to follow instructions and present its knowledge nicely, leveraging the intelligence already there. More about presentation than deep learning.
But even SFT isn't always enough for complex human values, right? Nuances, ethics.
Exactly. Humans often can't perfectly articulate all preferences or label data for every edge case. That's where learning from human feedback, or RLHF, comes in, a crucial step for deeper alignment.
RLHF. How does that work? It doesn't rely just on labeled examples.
No. Instead of explicitly coding rules or labeling everything, we teach the model to infer our preferences. This involves training a separate, specialized model called a reward model.
A reward model, acting like a human judge.
Essentially, yes. It acts as a surrogate, scoring LLM outputs based on human preferences. It learns to reward good responses and penalize bad ones.
How does the reward model learn our preferences?
It's trained on human-labeled rankings. You give human annotators several different LLM responses to the same prompt and ask which one is better, which is second best. The reward model learns from these comparisons, learning to predict human preference.
Okay. But reinforcement learning often deals with sparse rewards, right? Feedback only at the end.
That's a major challenge. Human feedback is typically sparse. You like the final answer or you don't. You don't usually rate every word. This makes optimization tricky, leading to techniques like reward shaping, adding intermediate rewards, or curriculum learning, starting simple.
And there's the risk of reward hacking, the LLM tricking the reward model.
A fascinating and tricky problem. The LLM might find shortcuts to get high reward scores without truly being helpful or honest, like the student copying homework. It exploits flaws in the reward model's understanding of the real goal.
So how does the actual reinforcement learning part work?
Okay, so the LLM itself is the agent, making decisions, predicting tokens. The environment is the framework where it interacts and gets feedback. The reward is the score from that reward model we just discussed.
Guiding the LLM's learning.
Exactly. The LLM's policy is how it decides the next token, its probability distribution. This policy is then optimized using advanced RL algorithms, often proximal policy optimization, PPO, which helps keep the training stable.
And we can apply chain of thought to alignment too. Process-based human preference alignment.
Yes, extending continuity. Instead of just judging the final answer, you supervise the model during its intermediate reasoning steps.
So for that math problem, you check each step the LLM takes.
Correct. A human or another verifier checks each step for correctness. This is different from outcome-based feedback, which only cares about the final answer. Process-based feedback penalizes mistakes in the reasoning path, even if the final answer happens to be right.
Finer-grained supervision, teaching the right way to think.
Exactly. It helps learn robust reasoning.
Is there a simpler alternative to full RLHF?
Yes, and it's remarkably effective. Rejection sampling. You generate multiple outputs from the LLM for a prompt, say, 10 different responses.
Yep.
Then you use the reward model to score them all and select only the best ones according to human preferences.
I'm done.
You use these high-quality preferred samples to fine-tune the LLM again, using supervised fine-tuning, SFT. It reinforces the desired behaviors. Many production LLMs actually use this because it's often simpler and more stable than full RL.
All this sophisticated training highlights the critical importance of data quality, that old saying, garbage in, garbage out.
It's absolutely fundamental. High-quality data is paramount.
And the challenge is a lot of training data comes from web scraping.
And the internet contains, well, everything. Errors, toxic content, fabricated facts, even other machine-generated text, which can create weird feedback loops.
Right.
Training on unfiltered data is harmful, leads to biased, unhelpful, wrong outputs.
So improving data quality, filtering, cleaning, that's essential.
Absolutely essential. Painstaking filtering and cleaning steps are part of the workflow. Researchers consistently show that sophisticated data processing deduplication, quality filtering, removing personal info significantly enhances model quality. Sometimes smaller models on cleaner data outperform larger models on raw data.
Let's shift gears now into the engine room. Once models are trained and aligned, how do they actually run? Inference basics. When the LLM takes a prompt and generates output, the use phase.
Right. At its core, LLM inference usually follows a two-stage process.
Right.
The pre-filling and decoding framework.
Pre-filling first.
Yes. Pre-filling, like encoding. The LLM processes the entire input sequence to your prompt all at once. It builds an initial context representation stored in the key value, KV cache.
KV cache, okay.
This phase is usually compute-bound, heavy on calculation.
And then comes decoding, the generation part.
Exactly. The LLM generates the output token by token, sequentially. It relies heavily on that KV cache built during pre-filling to maintain context. Decoding is generally memory-bound, lots of data transfer from memory for each new token.
And both are autoregressive. Each step depends on the last.
Correct. Builds sequentially. Now, when decoding, the LLM is solving a massive search problem, trying to find the best sequence of words.
But searching all possibilities is impossible, right? Too many choices.
Astronomically large number, computationally impossible. So, practical algorithms prune the search space efficiently.
The simplest is greedy search. Just pick the best token each time.
Yes. Simple, computationally efficient. At each step, picks the single token with the highest probability. like always taking the immediate best option.
But the downside is it can be suboptimal overall.
Often, yes. A locally best choice might lead you down a path that isn't globally the best sequence. High-quality options might get pruned early, like taking the fastest road initially that leads to a dead end.
So for better quality, we use beam search.
Right, beam search explores multiple paths simultaneously. It keeps a beam of the K most promising sequences at each step, say, the top 5 or 10 best options.
Exploring multiple futures at once.
Exactly. It's more computationally intensive, but generally gives higher quality, more coherent outputs.
And for more diversity, especially creativity, sampling-based search.
Yes, introducing controlled randomness.
Temperature sampling is key here. Adjust the creativity. High temperature, more random. Lower probability tokens chosen. Low temperature, more focused, deterministic, sticking to high probability tokens.
Okay, and top case sampling?
Limits the choice. Selects the next token only from the top cake most probable ones. Cuts off the long tail of unlikely, potentially nonsensical words.
And even more refined is top sampling, or nucleus sampling.
Very clever. Selects from the smallest set of tokens whose combined probability exceeds a threshold p. Prevents choosing weird, low probability tokens, but allows more dynamic diversity than fixed top case.
Sometimes you need more direct control, though, using decoding with penalty terms.
Yes, modifying the objective during inference to discourage bad behavior.
Like a repetition penalty, to stop it saying the same thing over and over. Exactly, a common problem. Or a length penalty for tasks like summarization, ensuring a specific output length. A diversity penalty encourages variation, especially in beam search. And constraint-based penalties enforce specific content or style rules.
Now for real speed optimization, there's speculative decoding. That sounds cool. How does it work?
It's inspired by speculative execution in CPUs. It uses a smaller, much faster draft model to quickly guess several next tokens.
A quick guesser.
Right. Then, a larger, more accurate, but slower verification model checks these guesses in parallel. If the draft guesses are good, matching what the main model would do.
You accept multiple tokens at once, super fast.
Exactly. It skips many sequential steps. If the guesses are bad, it just falls back to the main model generating one by one, like an intern drafting and expert verifying quickly. Accelerates things dramatically when it works.
Okay, so even with clever decoding, running these huge models efficiently needs more engineering. Efficient inference techniques for speed and memory.
A big one is more caching, optimizing that KV cache. It grows linearly with sequence length, becoming a huge memory bottleneck for very long sequences, potentially maxing out GPU memory.
How do you fix that?
Techniques like sliding window attention use a fixed size window. Cache only the most recent or relevant local context, not the entire massive history.
Makes sense. And batching, processing multiple requests at once.
Crucial for throughput, but standard batching often wastes computation by padding shorter sequences in a batch to match the longest one.
Like the carpool waiting for the slowest person?
Exactly. So we have continuous batching or dynamic batching, much smarter. It overlaps pre-filling and decoding for different sequences within a batch. Keeps the GPU constantly busy, maximizing utilization.
And disaggregation, splitting prefill and decode onto different GPUs.
Yes, reduces interference between the compute-bound prefill and memory-bound decode stages. Allows better batch filling, but needs a fast network to transfer that KV cache between the GPUs.
And for really long individual requests blocking others, chunked prefilling.
Right. Splits long inputs into smaller chunks during prefilling.
Yeah.
Prevents one long request from monopolizing resources, reduces latency variation, improves responsiveness.
Beyond operations, model architecture improvements also help, right? Like layer normalization.
Absolute key. Layer normalization with residual connections stabilizes training for these deep networks. The pre-norm architecture normalization inside the residual block is preferred now, often using variants like RMS norm, as seen in Llama. Keeps signals stable.
And activation functions in the feed-forward networks.
Vital. They introduce nonlinearities. Without them, deep networks would just learn linear transformations, severely limiting their power to capture complex patterns. Prevents representation degeneration.
And I read that removing biased terms in some parts of the network can actually help stability. Seems counterintuitive.
It does, but models like Llama and Gemma do this. Removing biased terms in the affine transformations, like in FFNs, seems to simplify the learning dynamics and improve training stability for these massive models, despite slightly reducing theoretical flexibility.
And handling the sheer scale requires parallelization, both for training and inference.
Essential. Data parallelism is common. Each worker GPU runs the whole model on a different data subset. Simple, effective, almost n-fold speedup possible.
But if the model is too big for one GPU,
Then you need model parallelism. Split the model itself across devices, different layers on different GPUs passing data along.
but that can leave GPUs idle, waiting.
Yes, simple model parallelism is inefficient. That's why we have pipeline parallelism. Divides a batch into micro batches. These flow through the different devices in a pipeline, overlapping computation and keeping multiple GPUs busy simultaneously. Much better hardware utilization.
All this scaling effort is guided by scaling laws. The observation that bigger models, more data, more compute, better performance.
Generally, yes. It's a fascinating empirical finding. Performance often follows a predictable power law function of these resources. More usually leads to better results, up to a point.
But lower pre-training loss doesn't always mean better on downstream tasks.
That's a crucial caveat. A lower test loss indicates better core prediction ability. But final performance on user tasks also depends heavily on the fine-tuning and prompting steps. Their effectiveness can vary. Utility is more than just raw pre-training score.
Okay, speaking of scaling, adapting LLMs for long sequences is a huge challenge itself, that quadratic scaling of standard attention.
It gets incredibly expensive, fast, both compute and memory. And the KV cache growing linearly also consumes vast memory for long contexts.
How do you handle that sequence parallelism?
Yes. Instead of the whole sequence on one device, you divide the attention calculation across multiple GPUs, process different segments of a long sequence in parallel. Lets you handle much larger contexts.
And there are entirely new, efficient architectures for long context.
Definitely. Memory models go beyond the standard KV cache. They incorporate explicit memory mechanisms like FIFO memory buffers or a compressive transformer with separate local and long-term memories. More efficient storage.
And how the model knows where tokens are is crucial for long text, positional embeddings.
Absolutely critical. One approach is query key biases, like Alibi or FIRE. Directly add a bias to attention scores based on relative position, IJ. Simple, effective, works well for long contexts.
But my personal favorite is rotational positional embedding, ROPE. It sounds so elegant. Rotating vectors.
It is elegant, a brilliant idea. Instead of just adding a position number, ROPE works by rotating the token embeddings in high-dimensional space based on position.
Like a vector slowly turning along the sentence.
Exactly. This injects positional info while preserving the token's core meaning and magnitude. It naturally handles longer sequences and interpolates well to lengths unseen during training because the relative rotation between tokens stays consistent.
Very cool. And position interpolation, adapting to sequences longer than trained on.
Another clever trick. You basically scale down the positions at test time to fit within the range the model saw during training, then let it interpolate. Allows models to generalize to longer contexts with minimal fuss. Extends their practical reach significantly.
This raises a bigger question. What does understanding long context even mean for an LLM? Does it read every word?
Good question. Research suggests LLMs act as powerful in-context compressors. They can summarize and distill information effectively from long inputs. They don't necessarily read like humans, but they extract salient points.
But the need for full recall depends on the task. Summarization versus finding a specific fact.
Precisely. Summarization might only need the gist. But retrieval-like tasks, finding that one specific sentence in a 100-page document, require the LLM to effectively memorize or retain access to the whole context with high fidelity.
Okay, finally, let's touch on inference time scaling for reasoning. For really complex problems, multi-step math, logic puzzles, let's think step by step might not be enough.
Often not enough on its own. Real reasoning is messy trial and error, backtracking, self-correction.
So you need ways of generating and verifying thinking paths? Using a search algorithm?
Yes, defining how the LLM explores possible solution paths, like a human trying different approaches.
You can have solution-level search. Generate whole solutions, then verify.
Right. Generate complete thinking paths, then use a verifier, maybe another LLM, to pick the best one. Can be seen as exploring a tree of possible solutions.
More fine-grained, step-level search with verifiers.
Yes. Guidance and pruning happen at intermediate reasoning steps. If a step looks wrong, the verifier flags it. The LLM backtracks and tries something else. Similar to beam search, but for reasoning steps, not just tokens.
Yeah.
Allows dynamic error correction.
And beyond these inference time methods, there's training-based scaling, actually training the model to be a better reasoner.
Yes. Further training to instill stronger intrinsic reasoning capabilities directly into the parameters. Takes more compute, but can lead to more robust reasoning, often combined with training-free methods for even better results.
Wow. Okay, so today, We really peeled back the many layers of LLMs, from that fascinating self-supervised pre-training, absorbing all that knowledge.
To the clever prompting techniques guiding their intelligence, turning data into conversation.
We explored the critical challenge of alignment with human values via feedback like RLHF.
And dove into the incredible engineering, making inference efficient, handling long contexts, performing complex reasoning.
What's fascinating here really is how it combines fundamental linguistic statistics with just cutting-edge engineering at an absolutely massive scale.
It's a testament to how knowledge, structured and applied with ingenuity, leads to truly transformative technology.
So what does this all mean for us, for you listening? As LLMs get better at self-correction, multi-step reasoning, even using tools, how might this change our own approach to learning, problem-solving, maybe even creativity?
It's a profound question. What new forms of thinking will emerge from these increasingly sophisticated systems? And how will they shape our future interactions with AI? Lots to think about.